Hello everyone. Last class we have actually discussed what metastable phases are, stable phases are, right, so how G versus T irrespective of how many phases exist, sorry, G versus composition at a given temperature irrespective of how many phases exist can tell you what the globally stable phases are and in which composition ranges, right. So, in this class we are actually going to use this to construct phase diagrams. Now, by phase diagrams I actually mean temperature versus composition phase diagrams, or what are called binary phase diagrams. We will not complicate it by looking at more compounds than just more components than just two components, right. So, T versus X2, right, and what is T versus X2? Essentially I have at every temperature I have G versus X2, and this is going to give me which phase is stable at which composition range. Okay. Then I am going to track the globally stable phases as a function of composition as a function of temperature. So, by changing temperature. And eventually I am going to plot the locus of it as T versus X2, and then you see some alpha phase is stable here, beta phase is stable here, something like that will come out, right. So, I mean this is not exactly correct, but so something like that will come. So, we will track the locus of stable phases. Okay. So, let us start with an example. Okay. So, I have a liquid to solid transition. Okay. Or I mean I can also call it alpha to beta, but that does not matter, so my material, it is an ideal solution in liquid to solid phase transition of 1 and 2, right. So, components are 1 and 2. 1 and 2 form an ideal solution in liquid, they are also ideal solution in solid. Okay. Now, what is an ideal solution? I am just going to write that G of liquid is equal to x1 mu 1 tilde of liquid, that is pure, right. So, this is of course dependent on temperature, x2 mu 2 tilde of liquid at again that given temperature plus kBT x1 ln x1 plus x2 ln x2. Okay. And similarly, G of solid is x1 mu solid, so this is mu 1 in solid phase, right. So, that is pure solid of 1 plus mu 2 solid, pure solid of mu 2, the second compound. This is platinum, just pure platinum solid, this is pure platinum liquid, right. So, this is the chemical potential in pure palladium solid liquid, this is the chemical potential in pure palladium liquid solid, right. So, kBT x1 ln x1 plus x2 ln x2, right. Now, so how do they look like? Right? So, they may so if I do not have x1, if I do not have this term, right, both of them are the same, right. So, G of S and G of T are the same, but this term is going to add and subtract a bit, right. So, it is going to skew it a bit, right. So, now at temperature, and they have the same curvature, right. So, curvature of GL and GS are the same, that you can actually check, right. So, they will have similar, so they may be tilted a bit, but they will have sort of similar curvatures. Okay. So, that is important. Okay. So, I will tell you why that is important. All right. So, now at high temperatures, let us write with a red pen, and this high temperature is T larger than, okay. So, let us say the melting point of 1 is, let us say, less than the melting point of, this is pure 1 and this is pure 2. Okay. Now, I am at a temperature where TH is greater than TM1, right. Now, at TH greater than TM1, okay. So, if I look at G versus X2, now G of liquid, so we know that liquid wins, right, and this is greater than TM2, not TM1. This is a material with a larger melting point, and I am at a temperature, this is material of this is pure 2, right. So, pure 2 has a larger melting point than pure 1, and then we are going to mix them to form solution. So, ideally this solution should have some melting point between TM1 and TM2, right, that is the idea. But I am at a temperature which is larger than the larger melting point, right. So, it should be I should, even if I form a solution, that should be the liquid that wins, and indeed liquid wins. If I look at it, so it is going to be, this is G liquid, and this will be so with some other curvature, some other slope, some other tilt rather, right. So, I will have G alpha, or this is G solid. Okay. So, at high temperature G liquid is less than G solid. So, what is it, liquid wins. Okay. Now, I am going to change the temperature. Now, temperature is equal to TM2, right. At temperature equal to TM2, so I have a solid which goes and hits here, and then I have a liquid, mostly liquid is stable, right. So, at all the temperatures, at all the compositions, except here the stability becomes equal, right. So, this is T equal to TM2, and this is X, so X2, this is pure X2, right. So, this is X1, pure X1, X2 equal to 0, this is X2 equal to 1. At X2 equal to 1, because which means I have a pure palladium, palladium has a larger melting point than platinum, right. So, there of course, I am at the melting point, right. So, where the G of solid equal to G of liquid. At all the other cases, in all the other cases, still liquid is winning, right. So, because I am still above the platinum melting point, right. So, pure platinum is still above this, right. So, in pure platinum case, the liquid is still winning over solid, right. So, here in the composition phase diagram, if I go along composition, only at X2 equal to 1 I have a liquid solid equilibrium, but in all the other compositions the liquid wins over solid, right. So, that is how you interpret this. Okay. Now, I am at a temperature where TM1 is less than T is less than TM2, I am still reducing the temperature, right. So, when I reduce the temperature, so this is going to change again, right. So, and this is solid, but now you see, so this is this is liquid, but now the solid, okay. So, here I am still not at platinum melting point, so I am still above the platinum melting point. So, liquid is going to win here, right, but I am below the palladium melting point. So, solid is going to win here. So, I will have some curve which is going to be like this, I mean the curvatures are going to be the same again, right. So, let us keep that in mind, that the curvatures are going to be the same, okay. So, maybe I will have some drawing issues, but I will try to manage, okay. Okay. Now, we are talking, right. So, here I have a solid, this is a liquid, the red one is a liquid, the green one is a solid, two different phases, right. So, now what is a stable phase? What is not a stable phase? We have exactly done these kind of diagrams earlier, right. Alpha, beta, right, both of them are intersecting each other, and if both of them are intersecting each other, I have a recipe to understand what is the global stability, and that recipe is so until here I will let the liquid phase win, right. So, and okay, let us just go back to this orange thing. So, until here I let the liquid phase win, from here to here I have a tangent, a common tangent where I have liquid plus solid, and from here I have a solid phase that wins, right. So, this is how we have constructed these diagrams. So, until this point, let me use this pen now. So, until this point I have a liquid phase, from here to here I have liquid plus solid, and from so from here to here I have a solid phase, right. So, I have a phase coexistence, I have some composition range in which there is a phase coexistence, okay. And so essentially this is moving up, this is moving down, right. So, relatively this is moving down, that is what is happening, right. So, eventually this point comes. So, this point where these two intersect is going to just shift more and more to the left, correct. So, eventually when I am at t equal to Tm1, right, I will be so the solid mostly is stable, this is solid now, but the liquid is just going to compete with the solid at this temperature, but everywhere else it is again not the liquid, right. So, I have only one point where liquid plus solid can exist, in the rest of the points it is just the solid that is stable, okay. And so below t less than Tm1 the solid of course wins. So, the liquid goes up now, right. So, it has completely flipped, the liquid is slowly going up, right. So, it is the same G curves that we are looking at, but since temperature is changing we are just so making the liquid go up and solid come down, right. So, that is what is happening. So, eventually they will flip, right. So, the solid is here and the liquid is there, right. So, this is the solid, this is the liquid, this is solid, okay. So, here again completely liquid dominates, okay. Now, we can put everything together now. Now, I am going to plot as a function of temperature and composition, and this is the phase diagram I am looking at, right. At high temperatures I have a liquid phase that is stable, at low temperatures I have a solid phase that is stable, okay. Now, in between, so at t equal to Tm2, right. So, this is Tm2 and this is Tm1, right. So, I have a liquid phase, I have a liquid plus solid equilibrium, right. Now, in between I will have so if I have a region, right. So, where liquid plus solid are stable, okay. So, at t equal to Tm1 so the way to interpret this we will see again. So, at t equal to Tm1 we have just the platinum, right. So, that solidifies at the end, right. So, at the lowest temperature. So, platinum will start melting, and then below Tm1 it is always the solid phase that is stable, right. Now, above Tm1, right. So, I will have a combination of liquid and solid phases that is forming, okay. So, this is how I construct the phase diagram, and so I can just call L as alpha phase, let us say L as beta phase and solid as alpha phase, right. So, L is in beta, solid is in alpha, okay. Okay, now so I am at this composition, let us say in the liquid phase I am coming down, I am coming down. So, what happens here? So, first I am going to spill out some alpha phase, right. Now, what is the composition of the alpha phase, right. So, that is what I am tracking, correct. Now, let us see, let us go back to my free energy diagram, and here I am asking you what is the composition of the alpha phase. Composition of the alpha phase is x2 alpha or x2 solid, which is here. Composition of the beta phase is x2 beta, which is here, correct. So, if I have to read off the composition of the alpha phase has precipitated out, right. So, at this composition, once I am at this temperature, right. So, alpha phase has precipitated out with a composition of x2 alpha, and x2 alpha is so it is gaining in material in palladium, let us say, okay. So, once so this is a uniform solution, a homogeneous solution, once I cool it down, right. So, here it has to precipitate out alpha, and that alpha or that solid has a composition which is given by this is x2 alpha, okay, or x2 of the solid, okay. Now, I cool it down further. when I cool it down further, right. So it's the G has shifted, right. So the G has now, so this point has further moved. If I look at this point has further moved, right. So in the next curve, if I just draw it, so this is the liquid, this now becomes the solid, right. So this point has further moved to the left, right. So it was somewhere here, it has moved to the left, and so so my x2 alpha and x2 beta also change, right. And these lines actually tell me what is the x2 alpha and what is the x2 beta as a function of temperature, right. So what is at this composition. So if I am just cooling down at this composition, liquid and solid, both of them coexist, but liquid has a composition of given by x2 beta, which is here, and solid has a composition given by x2 alpha, which is here, okay. But that is at that temperature, okay. So that is how you read off these phase diagrams, and these compositions are coming again from your G versus X diagram. G versus X at this temperature is going to say that liquid has this composition, solid has this composition, right. So this line I am going to call it, for a liquid solid transition, this line I am going to call it liquidus, and this line I am going to call it solidus, okay. And it does not need to be a liquid to solid transition, it can be some alpha to beta phase transition in general, where beta is the high temperature phase, alpha is the low temperature phase, right. And if I have just ideal solutions, right. So the 1 and 2 ideally mix in both alpha and beta, right. So the solution model is important here, right. So 1 and 2 are both ideal alpha and beta are both ideal solutions, right. Then I am going to have a phase diagram which is going to be like this, right. So here it is beta, here it is alpha, so 1 has a lower phase transition temperature than 2, right, and so this is what is called, and here I have an alpha plus beta, right, and this is analogous of liquidus, right. So whenever I am in this mixed region, I can read off the compositions by saying this is the x2 of beta phase and this is the x2 of alpha phase, okay. So that is at this temperature, at T1, right. So at T2 it is going to be something else, right. So the x2 alpha and x2 beta, this is the locus of x2 alpha, this is the locus of x2 beta, right, and this locus is coming from that common tangent construction when I look at G versus X diagrams, okay. So this is your first major temperature versus composition phase diagram, and this is called an isomorphic phase diagram. Why isomorphic? Morphic means similar structure, sort of, right. So I have 1 and 2 which are forming ideal solutions. So 1 and 2 should have, in solid they should have similar structures, the Hume-Rothery rules go by, so the Hume-Rothery rules can be applied, they should have similar sizes, similar structures, everything like that, and so as a result, so 1 and 2 are isomorphic in some sense, right. So these are what are called isomorphic phase diagrams, okay. Now if Tm2 is less than Tm1, then this phase diagram shifts like this, right. So you can just see that this is temperature versus x2, and the phase diagram is just going to be like this, okay. So here this is Tm1 and this is Tm2, right, it does not matter, right. So it is whether you tilt the phase diagram that side or this side, okay. So these are the so called isomorphic phase diagrams where the liquidus and solidus give you the trajectory or give you the locus of where so what is the composition of the alpha and beta phases, right. So this is for the beta phase, this is for the alpha phase once you start cooling the material, okay. So once you are in the phase mixture, okay, alright, good. Now alright, so that is your first phase diagram, but let us see where it is applied, right. So let us go back. So this is temperature versus this is the composition, right. I am going to just go back to, okay, what are the examples? Copper, nickel, right. So platinum, palladium, hafnium oxide, zirconium oxide. So all those things that follow ideal solutions, right. So ideal like solutions, they give you isomorphous phase diagrams. Okay, so these are some of the examples. Okay. Now this is the liquid state, this is the solid phase, this is liquid plus solid, right. And now I am going to so let us use this phase diagram and explain, so what is this business of what is called float zone technique, or not float zone really, but zone refinement. Okay. Now what is zone refinement? I have a material, I have silicon for example. Silicon, so I said it is impossible to make pure materials. So, so there are some impurities, right. I just want to see the impurity percentage. So, silicon is to start with 90% pure. Okay. So, let us say I start with silicon that is 90% pure, right. Now, okay, so this is the composition, this is 2 is silicon and 1 is the impurity, some impurity, right. Silicon is 90% pure, so so it is somewhere here, okay. And so it is 90% pure, so this is what is called a dilute solution, right. And dilute solutions, maybe I will show you later, are more or less so they follow isomorphic phase diagrams, right. So, if the solution is dilute, if A and B, right. So, I am looking at the interaction between A and B, but if B is very less, right. So, I can assume that this is just an entropic interaction. Okay. So, A bonds are so large, are so many in number that slight the differences so, and AB bonds are less, are very less, that enthalpic differences do not matter, right. So, A will just so AA bonds always overwhelm the enthalpic contribution, right. So, you do not have this differential contribution. AB bond strengths can be different, but they are so small in number, but that I can ignore it, right. So, of AB bonds is insignificant. In such cases, so it is entropic contribution dominates, and as a result I can always consider dilute solutions to be ideal solutions, right. And this does not need to even follow the Hume-Rothery rules, right. So, if I put some uranium in silicon in dilute proportions less than 1%, right. So, it will still form an ideal solution, okay. So, but uranium and silicon are completely different in sizes, right. So, and so that is okay, right. So, if it is ideal I can still assume that it is an if it is dilute I can still assume that it is an ideal solution, okay. All right. Now, so I am going back to this phase diagram, the isomorphous phase diagram, and I am actually starting. So, this is liquid, this is solid, let us see if this works, otherwise I will change it. So, I am starting here 90% silicon, I am starting at 90% silicon, right. And I want to make, the idea is to make silicon close to 100% purity, or I said 100% is not possible. So, 5 nines, right. So, 99.99999, right. So, this is 5 9 purity, okay, or 99.999. Okay. So, anyway, so 5 purities. So, I want to get to 5 purities. Okay. All right. So, what is the strategy? The strategy is as follows. I am going to first heat it up. Okay. It hits the solidus, that is okay. It goes into this phase mixture. I am actually that is fine, and I heat it all the way up to the liquid phase, right. So, the now liquid phase, right. So, silicon solid, which is 90% pure, is silicon, I am going to write 90% here, and this is in solid phase, is now heated to silicon liquid phase, also 90% pure. Okay. Now, I am going to cool it, right. Okay. So, now first when I hit the liquidus, right. So, now I am going to cool it. Okay. So, first I hit the liquidus. When I hit the liquidus, right, what precipitates out? What precipitates out is silicon, right, solid, which is much more purer, correct. So, this is about, let us say 90, it's you know, so the lever is much longer, right. So, it is about some 98% pure or something like that, right. So, I am going to you know, I hit liquidus where, you know, silicon precipitates, solid precipitates, but I made it actually 98% pure in some sense, right. Okay. But then if I start cooling it even down, right. So, then silicon starts, you know, increasing, or silicon starts becoming more and more impure, right. So, the liquid composition is this, the solid composition is this, but I keep on cooling it down, I come back to the same you know, silicon that I started with, 90% pure, right. I have somehow made silicon transiently more pure, right. So, this precipitated silicon was more pure, but by cooling it down I have come down, and then I have, you know, again brought back the impurities, right. So, here if you understand what I am doing, just by cooling it down to liquidus, T equal to T liquidus, yeah, so T liquidus at T equal to T liquidus, what did I do? I actually precipitated out more pure silicon, correct. So, you see, so there is silicon which has some impurities. So, what I did was, alright, so I will put all these impurities in the liquid phase, right, and I have created you know, so I have swept the impurities into liquid phase, and then, you know, so I have created a purer solid, right. That is what I did at liquidus. But then, like a dumb person, like an idiot, what I started doing, okay, so this is at the liquidus, okay, so this composition of silicon is more pure, that is okay, but I cooled it down even further because I have to cool it down, and by cooling it down, you know, so you know, more of impurities started going into silicon, right, from the liquid, and, you know, silicon started becoming more and more impure, and eventually, you know, silicon has come down to silicon of 90%. So, eventual cooling did not yield the desired outcome. Okay. So, what was I doing wrong here, right? So, once I found silicon which is more pure, right, if it is in equilibrium with liquid, of course, it will follow this phase diagram, right. So, if it is always in equilibrium with liquid, so if it is in equilibrium with liquid, it will follow this phase diagram, and then once I am cooling it, you know, so the liquid will start giving away more impurities to silicon, and I will of course end up at 90%, right. Somehow I have to disturb this equilibrium, right. Somehow once I get the more pure silicon, I need to disturb the liquid solid equilibrium that exists in the mixture, right. So, how do I do that? I have to remove the liquid. I do not want to put the liquid in contact with the solid, right. So, I have to remove the liquid. Okay. Now, that is what, so I have to remove the liquid or remove the solid from the vicinity of the liquid. I physically separate them, right. Then there is no liquid to give impurity to silicon, right. So, then there is no liquid from which silicon can get its impurity. Okay. So, now let us imagine I am going to do that, right. So, I will tell you how people actually do it, but so this is liquid, this is solid, this is liquid plus solid. So, I start here, I am cooling it, I have precipitated out this silicon, but then I have removed the liquid, right. So, now the second time when I am cooling it, I am just cooling it here. Once I remove the liquid, I have now made silicon 98% pure, right. Now, if I want to make it more pure, I again heat it up. Now, I am coming back here, right, and I again cool it, right. So, cooling is blue, right. So, once I cool it again, I am going to precipitate out 90, something like 99% or 99.9% or something like that, and I keep on repeating this process until I get to 99.999%, right. And you can see the increment in purity keeps on decreasing with rounds, right. So, I have to do it multiple times, but every time a silicon is precipitated, I separate it out or I remove the liquid. So, it is like so I take a broom, I sweep out the impurities, right, but I am segregating them out, right. So, I clean my floor, right. So, I keep the dust at a particular place, and that is my liquid phase, right, and I should separate it out, I put it in the dustbin or something like that, right, so that the rest of the solid is pure, the rest of the floor is much cleaner, right. So, I am sweeping out the floor, right. But for sweeping out the floor, it is not that I sweep and then put the fan on. So, if I put the fan on, again the dust is sort of redistributed. So, that is not what I should be doing. In the first strategy I was doing that, but actually I should separate out the liquid from solid, so that this liquid solid equilibrium does not exist, and once that does not exist, I mean, so then the solid becomes pure, more pure, more pure. So, then I keep on cycling it again and again, so that I keep on removing the impurities. Okay. Now, how do you do this? This is what is implemented in what is called zone refinement process, where I have a solid, right. This is a seed crystal, as they call, this is an impure solid, and I have to purify it, right. So, what do? I have all these LED lamps, right. So, that is going to locally melt the material, right. So, this material is melted using these, you focus these LED lamps using some parabolic mirrors and things like that, and then you melt this region, right. And so you have then gone from 90% into the melt phase, right. So, now you have to cool it, and the way you cool it is you actually start either you can move the solid or you can move the source, right. So, you move this melt away, right. So, essentially by moving the melt away, you are cooling down that region, right. So, that region, let us say I have moved, so I have done this by moving the solid has come here, very slow movement. So, this region which was melted now has solidified, but after it solidified, I am also slowly removing the liquid. I mean, so it is no longer in contact with the liquid, because the liquid region is somewhere else. I have moved this away from the the place where it should melt, right. So, the liquid region is elsewhere, right. So, by just thermal gradients, I am going to create a temperature here where I have physically separated out the liquid region from the solid region, right. So, I can then so then I am going to melt the next region, right. So, so this region let us say is always going to get melted, and then the solid gets drawn like this. So, every part of the solid has melted, the melt is removed to the next side, this has melted and then solidified, this has melted, the melt is removed, this has solidified, this has melted, this has solidified, this has melted, this has solidified, this has melted, melt is moved, so this has solidified, and so on and so forth. So, I start melting this side, which is where I start sweeping, right. I create a liquid, I take all the impurities from the liquid and then throw it away on the other side, right. So, and then on the other side, once that solidifies, I have a more impure solid here. Okay, I am going to cut that off. Okay. So, yeah, and then I do this again, right. So, and a second run where I melt this again, right. So, I put the impurities in the liquid phase, then move the liquid here, melt this, move the solidify this, move the melt, solidify this, move the melt, solidify this, and so on and so forth, right. So, I can move it by moving the bar or moving the LED sources. I should just check how they do it, but so all of a sudden I am again sweeping the floor or sweeping all the impurities from this side to this side, and eventually I collect all the impurities here and cut it off. Okay. So, like that I can make silicon which is 90% pure. In the first round I can make it 98% pure, very nice. Second round maybe 99.5% pure, very nice. Third round maybe 99.9% pure, and to get to that 99.999 I have to do it like 100 times or something, right. So, getting to the second digit, third digit becomes exponentially more harder, right. So, as a result so the purer it is, the more costly it is, because I have done this run many more times, right. So, I have used more time and more resources in the zone refinement technique to purify your silicon. Okay. So, this is a way in which materials are purified, right. So, it is a so called zone refinement technique, right. So, in which materials are purified, and it is a very standard technique, commercial technique. If you understand this isomorphous phase diagrams, it is easy to understand the zone refinement technique, right. So, you understand the phase diagrams and you have to actually construct this in your favor, right. So, if I am not removing the liquid, if I am just heating and cooling there itself, if I am not doing this physical motion of removing the ingot or removing the bar from wherever I am heating it, then I am not removing liquid from the solid, right. So, then I am still at liquid solid equilibrium. So, I can heat it and cool it, but nothing will happen at that region, right. I have to heat it, remove it, right. Then the solid that is formed is more purer than the previous than the solid you started with in that region, right. Similarly, the second region I heat it and then I remove the melt, right. So, then the solid that remains is more purer, right. So, that is how I implement it technologically. Okay. But if I just heat that region and not move anything, then solid is always in equilibrium with liquid. So, as the temperature keeps coming down, the impurities come back from liquid phase to solid phase, and I start with 90% liquid, I end up with 90% solid, right. So, that is not how it it works, right. So, you have to make thermodynamical phase diagrams work in your favor, and how do you make them work in your favor? You understand equilibrium. It is in equilibrium only if it is in contact, liquid and solid. Why do not I just remove the contact? And then solid has no liquid for it to gather impurities from. All the impurities are in the liquid phase, all the impurities are now in the dustbin, which is my liquid phase, right. So, once it is in dustbin, I will just give it to so the garbage collectors, and that is it, done, right. So, my garbage is gone from my house. Similarly, the garbage or the impurities are gone from silicon. Okay. So, and how did I do that? How did I evolve this strategy? By understanding the phase diagram, right. So, this is the simplest phase diagram of ideal solution liquid, ideal solution solid, but you can use it in zone refinement to do all these sorts of nice processes. Okay. So, with that, let us end here, and in the next class we are going to not look at ideal solutions anymore. We are going to go to some so the other solution we have done is regular solutions. So, we are going to look at regular solutions. What if we have regular solutions? How do these phase diagrams change, right? So, ideal solutions, nice isomorphic phase diagrams, right. So, in regular solutions, how do these solutions these phase diagrams change? That is what we are going to look at in the next class. Okay. All right, see you in the next class.